with step questions, it's usually better not to jump right in and start solving without having a look at the whole question. One, because you want to determine whether you feel like you'd be able to give it a good go, and two, because there tends to be hints later on in the question about how the question is structured. So let's have a look at some of our first thoughts when we look at the question one. So I see immediately that we have to show a result and then afterwards apply that result to some examples. It doesn't say explicitly that we have to apply that result, but more often than not, if you're asked to show something at the beginning, it will have some application later on. We're using substitution. There's a condition here that will be important if we look at part IB, we can see that one of the limits is negative, which means that we have to make sure that we consider that. Then part 3, we've got to show another result. But all of these are definite integrals past the first part. So with that in mind, let's think about why showing this result is useful. Because we've got an integral and a seemingly more complicated integral afterwards, where we have variables in both the numerator and the denominator. So let's have a look at why this integral looks, well, it looks worse, but let's think about solving this, because later on there's definite integrals involved. So we want to think about why this form that we've got here is easier to solve than the form above. Okay. So we could go ahead and use substitution. So we could use substitution again of u equals 1 plus t squared, because then we would get du by dt is 2t. That would then cancel this t, and we would get quite a nice integral moving forward. However, we used substitution right at the start, so that's probably not the way to go. Thinking about this more intuitively and annoyingly for some questions in STEP, intuition is really important. So let's say we have an integral, an indefinite integral of a function. The answer is going to be another function, so we can call that g of t. Now, if we take the derivative of both sides, then we've got an equation that looks like that, which then gives f of t is a derivative of some kind. So maybe it would be easier for us to think about what we would have to differentiate in order to get our function that is inside of here. So let's have a look at that then. Let's start with the awful function in the bottom. We know that it's raised to the power of 3 over 2, but it's on the denominator, so that's a negative 3 over 2. When we're differentiating, we obviously drop the power by 1. So our original function would have to start with negative a half as the power. So let's see what happens when we take the derivative of this. So we get negative a half, 1 plus t squared to the negative 3 over 2. And because we have a function of t inside the brackets, we have to use the chain rule and multiply that by 2t, which, if we simplify that, so we multiply those two things together, that gives us negative t, 1 plus t squared to the negative 3 over 2, which happens to be what we have in our integral at the top. Happens to be what we have here. So therefore, we know that this equals 1 plus t squared to the negative a half evaluated put the square brackets around it. Evaluated at the limits of our integral. So with that being said, we can now move on to the later questions. I think that one of the reasons for making these videos is to go a bit more in depth than just providing you with a solution, because a lot of step questions, with step being aimed at the top 5% of students or something around there, it's all about the thought process, and that's the type of thought process that you would typically have as you answered the question. So instead of doing it right at the beginning, those are the type of things that you would probably end up noticing as you go through the question. Into answering part 1 of the first question. So we have a function that we've got to use substitution with. So I'm gonna write my substitution in the top right. We've got x equal the 1 over t, which implies dx by dt equals negative t to the negative 1 over t squared. Now that's because we've got t to the minus 1. We multiply by minus 1 in the front and drop the power by 1, which gives us negative 1 over t squared. Now let's take our integral. So we've got integral from a to b. Those are constants in x of 1 over 1 plus x squared to the 3 over 2 dx. Now let's use our substitution and put this in terms of t. So our limits, I'll come back up into this top right corner. Our limits when x equals a equals 1 over t implies that t equals 1 over a, or a to the negative 1, and then because these are just dummy variables, we have the exact same. The upper limit So we can then write this as the integral from a to the negative 1 to b to the negative 1 of 1 over 1 plus, I'm going to write this explicitly here, and then we want to multiply that because we have dx. I'm just going to write a little aside here in green. We'll move over to the right here, and I'll just write it on this right hand side. Usually when we're doing substitutions, we would have something like u equals 1 plus x squared, which then gives us du by dx to be 2x. But because we're changing from the dx world to the du world, we have to take we would then take du. We would then need to know what dx is. So not du, we would then need to know what dx is. Which when we rearrange, we would get 1 over 2x du equals dx, and then we would replace our dx with what was on the left. However, in this example, we're actually just replacing x on its own. So we have, at the end, we have our integral dx, but we want this to be dt, right? So we know that dx by dt gives us dx. So in this case, we don't have to take 1 over. We don't have to take 1 over what we've worked out there. That might trip some people up because of the way the substitution was chosen. But in this case, we just have dx by dt, and I'm writing this out as explicitly as possible. So we then get, on the denominator, we get 1 plus 1 over t squared 3 over 2 multiplied by negative 1 over t squared from before dt. Simplifying this and taking a look at the form we need it in, we need to get a t into the numerator. So if we take a look at our denominator again, we've got 1 plus 1 over t squared, which can be written as t squared over t squared plus 1 over t squared, because this just equals 1. And then we get t squared plus 1 over t squared. And then we can take our denominator out and put it into the numerator. So that means that on the denominator we have, let's take the t squared out as we just worked out, to the power of 3 over 2. Sorry, that should be a negative, but I don't have space. Let me rewrite this. So we get t to the negative 2, because it was on the denominator, 3 over 2, and then 1 squared. 3 over 2. Almost. So we've got the negative from the dx by dt multiplied by 1 over t squared dt. And then the final step, we bring it all together. We've got our limits. And then multiplying these powers together here, that gives us t to the negative 3. So, put that into the numerator. We then have 1 plus t squared 3 over 2 multiplied by t squared dt. And then cancelling out our numerator and denominator terms, this gives us our required result. And that is how we show the first part of the question. Throughout this example, I'm going to be doing working out on the right hand side just so you can see my thought process. A lot of people won't need a lot of this working out. Different people are able to do different things in their head, but when you have time in exams such as STEP, you do get a lot of marks for showing that you know what to do. You get partial credit even if you get things wrong. So it is worth doing some of these extra steps. Now moving on to part 2 of the question, what I will do to start with is write out the result that we just proved. As I pointed out before, and I'll just scroll up so you can see, we do have that condition. Thankfully, for this example, the condition is fine because we've got b equals 2, a equals a half, b is greater than a, greater than 0. So let's actually answer this question, noting that before we actually worked out what this was, and it ends up being 1 plus t squared to the negative a half evaluated at these values. So let's take first part. Let's choose a equal half, b equal 2, and our integral, which is now going to be as simple as a couple of lines. We know that this equals a half to negative b 1 plus t squared to 3 over 2 dt, which can then be evaluated at our limits of a half and 2. I'm gonna move back over here. So we have 1 plus a half squared to the negative a half minus 1 plus 2 squared to the negative a half, which gives us 5 over 4 negative a half minus 5 the negative a half, 1 over square root 5 over 4. This 1 over the square root of 5. Which, again, I'm going to write this out explicitly. So this can be written as following. Which means we get 2 over root 5 minus 1 over root 5, because here we know that 1 over a over b over a, and that's what's been used there. Out. And some people rationalize the denominator and others don't. I personally like to. So we have that equals 1 over root 5, which 2, 5. It's not equal to that. It's equal to root 5 over. And that is the second part answered. Now looking at part B, we've got our second part to the question. Like that. And we know from our result over in the right hand over here that this can be written as 2 times the integral before and then, because this is a constant, we can move it outside of the limit. That doesn't matter. So we've got 2 times the limit epsilon to 0. Now that is the form, but we know that this changes into the t world. So got the same. We take the reciprocal of our limits because we're applying the same substitution to that function. So we've got a half and 1 over epsilon of negative t over 1 plus t squared 3 over 2 dt, which, as we know, gives 1 plus t squared half, and we evaluate that at our limits. Now, from the previous part, let me just scroll back to it. We already had here. We already had an upper limit of a half, and that same upper limit there, then here, then here, then here. So we know that it's 2 over root 5. So we can immediately write that one as 2 over root 5. And now we need to deal with our limiting. We need to deal with the limit case. So we've got 1 plus 1 over epsilon squared, all square rooted. also, with an expression like this, if limits are additive, so we can take our, let's say we have the limit. I'm just working over here on the right hand side. So we have the limit of a function of epsilon minus another function of epsilon. That is the same as the limit of the first function minus the limit of the second function. That works the same. And we can see in our first function there isn't an epsilon at all. So we're only now dealing with this limit here. So moving across to the side, we need the limit of epsilon tending to 0. The limit as epsilon tends to 0 of 1 over square root 1 over epsilon squared. Now, as epsilon, we'll write this, we'll try to write this proper English. As epsilon tends to 0, 1 over epsilon squared, what does that tend to? So if the bottom is tending as close as it can to 0, then that's going to get massive and tend to infinity. Therefore, as epsilon tends to 0, 1 plus 1 over epsilon squared tends to infinity. Then when we square root it, we have the same. And then we have 1 over something that's tending to infinity, which gives 0. So now we have 2 times the limit. Well, we don't actually need to put the limit on this. Just worked it out. We've got 2 times 2 over root 5 minus 0, 4 over root 5. Or if you want to rationalize the denominator, 4 root 5. And that is our answer to that question. It was a bit more involved. We had to use this limiting behavior. But if you didn't want to use that, you could use any method. Because as you can see here, it says evaluate. And when it's evaluate, you can use whichever correct methodology you want. Yes, it was easier to use what had been given before. However, you could have used whichever substitution you wanted, a trig sub, u equals 1 plus x squared, whatever, and you would have come, hopefully, to this same answer. Now we're on to the final part 3 of the question. And we just zoom in and have a look at the question for a second. The integral that we're trying to solve or show, we've got to show that it equals one thing, then something else, and then by showing that, evaluate an integral. Right? So let's see if we can make any progress with this question at all. And I can assure you we will with just a bit of thought. We've got a 1 plus x squared on the bottom, all squared, and a 1 on the top. And if we go back to our original question, we had a 1 plus x squared, 3 over 2 that time. But the form of the integral is the same. The form of the integral is the same. So if we were to use that same substitution that we used in the beginning, And I'm going to start up in the top right here, and we'll move our way down. We've got our integral with limits that they match our condition from before, our b greater than a greater than 0. And if we use the same substitution of x equals 1 over t, we're gonna get our bottom limit here is going to be 2. Our top limit is going to be a half. We're then going to get 1 over, and I'm trying to do multiple steps at once here. This step here is very similar to the step before. The only thing that is different is the squared power in the denominator rather than it being 3 over 2. So if we follow that in the same process and use the blueprint of before, we're going to get t to the negative 4 because it's on the denominator, so it's a minus 2. We get our 1 plus t squared squared. Apologies. That's a minus. And we've got 1 over t squared, which then gives us t squared on t to the 4 on top, multiplied by t to the negative 2, coming from our dx by dt term, all over 1 plus t squared dt from half. And we've got our negative there, which then equals, take the negative out the front, that'll be a power. The reason we're doing that is because we're looking to get our integral in this form. So we've got a t squared on the top, and on the bottom we've got a 1 plus t squared dt. Now let's have a look at the differences between this form here and the form that we've got. The first thing I noted is the limits are the wrong way around. We've got a negative at the front, and it's in terms of t rather than x. However, a negative on the outside means we can change our limits round. We change our limits like that. And whenever you have variables, you can call them anything. We could have used A, B, C, D, any of the Greek letters. It's just a placeholder. So this t, let's let t equal x be our substitution, which means that our dt by dx is 1. So we're only multiplying by 1, which means it stays the same. So we're allowed to just write x in for t. And then we've shown the first part of that question. I'll just leave that there for a second. This bit, it's called using a dummy variable if you want to do extra research into that. Dummy variables, all it is a placeholder. You can replace it for whatever you want. But when you do the substitution, you need to take into account the dt by dx or whatever letter that you use. So we've done this first bit. We can tick that off. Now the second bit. Slight issue there. How do we make that? How do we gain that from what we had before? So there's a reason we had to show the bit in the middle first. So going continue. So we're going to continue here. If we know that those two things are equal, and we see we've got a half on the outside, then a 1 plus x squared has disappeared. Where do we get that 1 plus x squared from? We've got a 1 here, and we've got an x squared there. So can we combine these two integrals at all? Yes, we can. So I'm going to write this out as explicitly as possible. Our original integral on the left-hand side can be written as half of that integral plus half of the integral again. As we agree, we add half of the same thing together, we get the whole thing. So with that bit in mind, I'm actually going to move down here. With that in mind, what I'll do is I'll rub this out, and then we can start below, and then I'll do some working out if I need to. So we can then write back to the thin pen, and then write our integral 1 over x squared dx as half of itself plus half of itself again. So this is where the halves come in. But if we discard the half for a second, we know that this, well, the whole integral, is equal to this. So let's change one. Let's change this last one. So that gives us, I'm going to write a bit smaller now. That gives us the integral that we had, plus the same integral that we just used of x squared over 1 plus x squared squared. Now, the reason why that's important is our limits are the same. What we're multiplying by in the front is the same. So we can just add the two integrals together. So we get half. We're integrating over the same limit. The denominators are the same, so we get 1 plus x squared all over 1 plus x squared dx, which gives us half times the integral from a half to 2 of 1 over 1 plus x squared dx. Now, because we've shown these two parts, we've now got to evaluate. And we're evaluating this. We're evaluating our integral from the beginning. But we know that our integral from the beginning, here, can be written as the integral at the end. So therefore, what I'll do to write it explicitly, you've got the integral of to 1 over 1 plus x squared dx is equal to a half times the integral that we just showed. And this integral is a lovely one. It's arctan x, which is used a lot in step questions. So remember that. Then that equals a half times arctan x of 2 minus tan. So arctan of 2, not arctan x of 2. Arctan of 2 minus arctan a half. And that is part A for that question done. Now for the final part of question 1. It's this daunting integral. And it's the final part of the question. It's probably worth in the region of 4 or 5 marks. So up to this point, you've probably gained 15 out of the 20 if you've got up to here with all the answers correct. So with that being said, let's think about this. What do we immediately notice? So the limits are familiar. One of the terms on the bottom is familiar. We have summation in the numerator this time. So how do we figure this out? The question screams familiarity. And it's the final part of the question, so arguably we will be applying things that we've learned in the question so far. So let's use that and use the substitution that we had, which gives dx of 1 over t squared, negative of 1 over t squared. Now, we need to be careful about our substitution, but we know that we can swap our limits around because it's the reciprocal. In the numerator, we have 1 minus 1 over t, which if we just go to an aside, 1 minus 1 over t minus 1 over t. In the denominator, we have 1 over t multiplied by 1 plus 1 over t squared, all square rooted, multiplied by our 1 t squared negative dt. Wow. Right. This is daunting, but let's simplify it and see if we notice anything about the integral. Because we might be able to use some of the forms that we've proven up to this point. So, using this, we then have that same integral, same limits of t minus 1 on the numerator, because we have, if I just expand this a bit more, this is t minus 1 times 1 over t. And we have a 1 over t in the denominator, so those can cancel. And using the same logic as we've been using all the way through, we have a t squared plus 1 to the power of a half. But we had a t squared on the denominator. I'll actually write that explicitly. So when we had 1 plus 1 over t squared, that's the same as t squared plus 1 over t squared, but we have it to the power of a half. So when we take it out, it's t to the negative 2 to the half. So carrying this on, we then also need to multiply the top by negative 1 from our dx by dt term, and multiply the bottom by t squared. Now, what has that done to help us? It looks like nothing. However, let's continue simplifying it. So the top's 1 minus t. Our t to the negative 2 to the half, that is t to the negative 1. But we have a t squared, and t squared times t to the negative 1 is t. We've got t there. Then we have 1 plus t squared to the half. Now, looking at this, we've not done anything. Using our dummy variable from before, remember we just changed t to x because we've got dx, well in this case, dt by dx is just 1. It doesn't really matter. This now means if we use our dummy variable again, we have the integral from 2 to a half of 1 minus x all over x plus 1 plus x squared to the half dx. Now, you don't have to be the most eagle-eyed to notice that this is the same as this, just with the limits swapped. So what can we do to change the limits back? Well, we multiply by negative 1, we change the limits, then we get 1 over x over x plus 1, x multiplied by 1 plus x squared to the half dx. So if we call our original integral I, we then have that I equals negative I. Therefore, our integral has to equal 0. Because our substitution just turned it into the negative version. And that is question 1 complete.